This is a reaction kinetics tutorial 2 presented by the SHRTV with reference Cambridge International ASA level by Laurie Ryan and Roger Norris. So we first start with the learning outcome. This is the learning outcome, so the student is supposed to pause the video and see every learning outcome for reaction kinetics 2. So now we first start with the factors affecting rates of reaction. We need to know that there are different factors affecting the rate of reaction. We have the concentration. These factors can be visualized inside the formula of rate. We need to know that the formula of rate is given as K, the concentration of the different reactants. So, and this concentration of the different reactants depends on the slow step of the reaction. These concentrations are taken from the slow step of the reaction, the path of the reaction that is going to be the slowest. So that's where you take the different reactants are going to control the reaction. The different reactants that control the reaction, they are at the level of the slow step of the reaction. So we first have the concentration of the reactant, as you can see from the rate formula. The next one, we have now temperature and catalyst. Temperature and catalyst are going to change the K, or the rate constant. We need to know that what the rate constant is equals to PZF, where P is the factor that controls the orientation of the atom, Z is the factor that controls the level of vibration, and F is the factor that controls the level of collision. So now F is given as A, which is the Arrhenius constant, e raised to the power negative EA, which is activation energy, all over RT. So that's why you need to know that since this activation energy, catalyst can also be used in affecting the reaction rate. So you see that catalyst is going to reduce that activation energy, thus is going to increase the rate of reactions. So in this chapter we have different definitions that we're going to visualize. Now let's see rate of reaction. You need to know the rate of reaction is the change of concentration with respect to time. So that's just how we define rate of reaction. So now we have different methods to visualize the rate of reaction. We can use sampling. This method involves taking a small sample of reaction mixture at various times and then carrying out chemical analysis on each of the samples. So we take various samples and then carry out each of chemical reaction. So we see that what in this case an example is alkaline hydrolysis of bromobutane. So we have this one. So a sample to take small sample of in which are taking place in chemical reaction. Take small sample, and then when you take that sample you quench it in order to stop or slow down the reaction by cooling down with ice. You cool down directly with ice, and then you visualize the color. So in this reaction here you see that you have this and you have bromide ion. So now you quench that reaction and then you can visualize either the color, you can also do titrimetry, or you can also do expansio or expansiometry, all these. So you can also use, so this is sampling method where you quench. So the other method is going to be continuous. In this method, a physical property of the reaction is monitored over a period of time. Some of the examples are using colorimetry. So you can use colorimetry, conductivimetry method, or measuring gas volume or gas pressure. So in case where you have gas which are being evaporated, you can use. So colorimetry can be used to monitor the change in color of particular reactant. For example, this method it can be used in this case of iodine. You need to know that iodine is dark red. Since iodine is dark red, in this reaction is going to become much more colorless as the reaction progresses, and you can now plot the color of the intensity of color against the time. So change in electric conductivity. Electric conductivity can be visualized from this. In this reaction, you see that there is no reactant that's capable of conducting current, and then here there is more product that is going to conduct the current. So you can use electroconductivity there. And the last one, you can also use densitometry. Densitometry, in order for you to see if the molecule is becoming much more the voluminous, it has a greater volume, the volume of the solution becomes higher, like in cases where you convert from let's say hydrogen bonding to now in cases of van der Waals forces of permanent dipole So now these are the different things. Now how do you calculate the rate graphically? So we take this example. So in order to calculate the rate graphically, the thing in order to do, you have to take this example and then you plot the graph. So you can just plot propane mole against the time. So when you plot, you need to know that what is the rate. Rate is just defined as the concentration of a particular reactant that control the reaction divided by the time. So now in this case, in order for you to know this rate, the rate are going to vary with respect to every time. You can have the rate at this position here. So this is the rate at the start of reaction, called the initial rate of reaction. So you can just draw a tangent to this line. You draw a tangent to this line, then you find the rate at initial part. You can also have rate at different points of reaction. You can have rate at this point, the rate at this point. In order to find the rate at this point, which is 20 minutes, just draw the tangent to that line, and then you find the gradient of that line. So after finding the gradient of that line, you can have the rate graphically. So those are the small method in order to calculate the rate graphically. So now we have other methods to calculate rate, like by using the rate constant and by using the initial rate of each reaction. So you can use initial rate of a particular reaction in order to calculate the rate formula of each reaction. So now this is the stoichiometry and this is the rate equation. You need to know that the rate equation, with rate equation you have this formula, and in this formula you have both n and n raised to the power of each of these ones here. And this m and n are called the partial orders, but n plus n is equal to the order of the reaction. So as we are going to see down here. So this is one rate formula. Rate is equal to K transition of hydrogen and transition of iodine. Here rate is going to be equal to that. Here rate is going to be equal to that and order. So now let's go to the order of reaction. The order of reaction show how the concentration of the reagent affect the concentration of the reagents affect the rate of reaction. The order of reaction is with respect to a particular reactant is the power to which the concentration of that reactant is raised to in the rate equation. So as you can see, so these are the orders of reaction. Order of reaction of this equation is going to be 1 plus 2, which is going to be equal to 3. So the total rate formula as a potential equal is given as this one. K, the concentration of A raised to the power n, the concentration of B raised to the power n, where n plus n is going to be the order of the reaction, and n only are going to be the partial orders. So you need to know that not every reaction, so in order to find this n and n, the partial orders of reaction, you cannot find it from stoichiometry. You don't find the partial order from stoichiometry. That is, in these reactions here like that, you see that NO here is, you see that all of these are the reagents, but you see that it's only depending on NO because NO produces the slowest step of the reaction. That's the first point. And then the second thing is that you see that the stoichiometry of NO here is 1, but here you see that the partial order is going to be 2. So this partial order does not depend on the stoichiometry that the molecule has on the Rayleigh balance equation, but instead depends on experiments. This is why here you have this stoichiometry as 1.5. So now from this equation, so you have these questions, these different equations. So now let's go now to find order of reaction. The different graphs of the different order of reaction. The zeroth order. For zero order, when you want to find the order of reaction in the graph, these are reaction rate. You just plot the reaction rate graph against the concentration of the reactants. The reaction rate graph, because order of reaction can be shown, is mostly shown from this formula. So the reaction against concentration. When you plot the reaction against concentration, the zero order just means that this power of n is actually the total order of reaction is only equals to, is going to be equals to 0. So the rate of reaction against concentration is going to be constant. Now first order just means that it means that the order of reaction is going to be n equals to 1. So it means that the rate is going to be equals to K, the concentration of R. The K concentration of R is just plotting the line y is equal to mx plus c, and you see that it's going to be a straight line also. And then you have the second order, which is the rate equals to K is squared with R squared, etc. You see that it's going to follow a these are the different graphs. So example you have the first order reaction is here, where you have dinitrogen oxide to produce nitrogen oxide in terms of gold. So you have this order is a first order reaction. For a zeroth order, you have ammonia producing nitrogen and hydrogen. So this one is going to be zeroth order. The rate only depends on the rate constant. And then you have second order for nitrogen dioxide plus carbon monoxide to produce nitrogen monoxide plus carbon dioxide. This rate is going to be equal to K, the concentration of nitrogen dioxide all squared. This square shows a second order. So these are the things to visualize here. So now if you plot now the concentration of the reactant against time for first, second, and third order, we're going to visualize what? The first zeroth order we're going to have this graph. For first order we're going to have this graph. For second order we're going to have this graph. Now you need to know that it is only the first order that has what is called the half-life of a reaction. And half-life is defined as the time taken in order for the concentration of the reactant to fall to half of its original value. So that is what is called half-life, and it's only found inside the zeroth order. You see that the half-life inside the zeroth order is not going to be constant. It's only in the first order that the half-life is constant. You see that during the first and half-life is very long, then the more you decrease, the half-life is becoming shorter. So the half-life is not constant in zeroth order, but in first order, half-life is same as this half-life here. So first order is going to be constant. And then for second order, half-life, you see that for this one is smaller compared to this one. So half-life is different also for second order reaction. So now let's calculate for rate constant. So to calculate for rate constant now, we just need to use the initial, like this example, we just need to use the initial rate of each of the equation. If you know the rate at a particular time, you need to know that K is going to be the rate all over the concentration at that particular time times rate of the concentration. If you know now there are different concentrations, then you know the rate at that particular time, you can now calculate the equilibrium, the rate constant. So now in order to calculate the half-life, just know that T half is equal to 0.695. That's the ln of 2 divided by the K, which is the rate constant. As easy as that. And this is only respected in cases where you are using a second order reaction. For second order reaction, the T half is going to be given as this, but for zeroth this is only used in first order reaction instead. Sorry, this is only used in first order, but in cases of zeroth and second order, we don't use this formula, because this is used in second and first order, because only in first order this is going to be a constant. So you see, I'm going to have T half is going to be the ln of 2, that is 0.693 divided by K. So now deducing the order of reaction from raw, here you are going to use data. Some data, you have data, let's say for hydrochloric acid, and you have data for this. So let's say that this and this are going to change, are going to affect the rate of the reaction. So you are going to use the partial orders. So in order for you to find the partial order, you can use now the initial rate of each of these reactions. You can use the initial rate of each of these reactions, and then you have their corresponding rate. So now when you draw those graphs and everyone, you have the rate and the initial rate and all that. So you can now factorize in order to have the different partial orders and then the rate of reaction. So now so these are the different things. So the rate determining step, as I've initially explained you, the rate determining step is the slowest step of the reaction, and so from that rate determining step that you find the different reactions that are going to affect the rate of the equation. And then in these reagents are the ones that are going to be found on the rate equation. So from here you say thanks for your kind attention, and please don't forget to like and subscribe the channel. Thank you.